Hello and welcome to another NGen Math 6 lesson by eMathInstruction. My name is Kirk Weiler and today we're going to be doing Unit 5, Lesson 5 on equivalent expressions. This is a critically important topic. Much of what you do in algebra, and I think this really escapes students, especially when they get to like higher levels of algebra, like high school level algebra. You know, much of what you're doing is just playing around with algebraic expressions to come up with ones that are equivalent to it. That gets oftentimes just lost in the mix, but they often are just doing manipulations to make equivalent expressions. Now, of course, that's all kind of foreign to you if you don't know what an equivalent expression is. So let's jump into it and take a look. All right, equivalent expressions. Two expressions are equivalent if they are equal to each other for every value of their variable or variables. Most expressions have only one variable in them, but the idea is like if I have two expressions and I pick any random value of x, or like in the first exercise n, anything like that, and I put it into the two expressions and I come up with their value, they'll have the same value. All right, now you might say, well, why don't we call them equal expressions? Well, equality is reserved really for just numbers, right? So when we talk about equivalent expressions, we really can't call them equivalent until we really know what the values of the variables are. So let's take a look at exercise 1 to get a sense for this. Consider the two expressions 3n plus 6 and 3 times the quantity n plus 2. In both a and b, evaluate the two expressions for the values of n given. Show your work. All right, so simple enough. By the way, anytime I see kind of an expression that's in parentheses like this, you'll always hear me say something like 3 times the quantity n plus 2. Because if I said 3 times n plus 2, that would sound a lot like what I said here when I said 3 times n plus 6, right? You couldn't really tell, but 3 times the quantity n plus 2. All right, so anyway, let's evaluate these expressions for a few different values of n, and let's kind of do some of them together. Let's take a look at letter A, 3n plus 6 for n equals 1. So if I want to figure out what that expression is, it's pretty easy. I just put 1 in for n, right? Order of operations says I have to do the multiplication first. That's real simple. And I'll eventually get 9 for that. Ah, so easy. So easy, right? And in fact, it's easy to do all of them. Let's do 1 for letter B, okay? And let's do n equals 1, and then we'll have you do the other 4 on your own. So for n equals 1 here, slightly different calculation. I'm going to put 1 in for n. Now my order of operations says I have to do the work in parentheses first, but that's simple enough because it gives me 3. And then 3 times 3 is 9. All right, easy enough, right? So now what I'd like you to do is I'd like you to figure out what the value of 3n plus 6 is for 2 and 3, and the value of 3 times the quantity n plus 2 for n equals 2 and n equals 3. Pause the video now and take a few minutes to do that. All right, let's go through it. n equals 2. Same idea, right? I'm going to put 2 in for n. I'm going to multiply 3 times 2, and I'm going to get 6. Then I'm going to do the addition. 6 plus 6, I'm going to get 12. When I put 3 in for n, I'll get 3 times 3 plus 6. 3 times 3 is 9. Then I'll do the addition. Plus 6 is 15. So 9, 12, and 15. Great. Let's now evaluate this one for 2 and 3. So very similar to before, I'm going to put the 2 in for n. I'm going to figure out that 2 plus 2 is 4, and then I'm going to do 3 times 4, which is 12. The last one, I'm going to put the 3 in for n. I'm going to get 3 then times 5, and 3 times 5 is 15. Now, this is just 3 examples of different values of the variable, but notice in each case, right, the value of the expression turned out to be the same for both expressions. And the really crazy thing about these two expressions is you could pick any value of n you want, from n equals 0 to n equals 10,000. And if you put it into this expression and calculated it, and put it into this expression and you calculated it, you'd get exactly the same value. Really remarkable. And that means that these two expressions are equivalent. Literally, That means if I was in some kind of larger algebraic problem, ones you haven't even gotten to yet, but if I was in some larger algebraic problem, I could replace this expression with this one if I wanted to, or I could replace this one with this one if I wanted to, because they're really the same expression. They just look a little different, that's all, right? So let's keep going with this idea of equivalent expressions. Now, really what happened in the last problem, was an example of what's known as the distributive property. Now you've seen the distributive property, you've even seen it before in this course, but just a little review, right? If A, B, and C represent numbers or variables, it doesn't matter because a variable is a number, it's just one we don't know, then A times B plus C is the same as A times B plus A times C. Right? So if I'm multiplying a sum, and it also works with differences, so if this was a subtraction, it would also work. If I'm multiplying a sum, I can multiply each part of that sum and then do the addition at the end. So let's see what that means when we look at exercise number 2. Let's look at the expression 2 times the quantity 5x plus 3. Letter A asks us to use the distributive property to rewrite this expression as the sum of two terms without parentheses. Show your steps. All right, great. This is a classic case of the distributive property because we have a sum of two terms inside of this parentheses, and we're multiplying by the number 2. Now you'll see a lot of math teachers that will do something like this. They'll draw little arrows like this to remind ourselves that what we're really doing is 2 times 5x plus 2 times 3. Now, in order to kind of simplify this a little bit more, well, 2 times 3, that's a piece of cake. That's just 6. But what do we do with this? Truly, this is 2 times 5 times x. And one of the great things about multiplication, one of the really, really wonderful things about multiplication, is it's what's known as associative. And associative means that when I'm multiplying 3 things in a row, I can multiply any 2 of them to begin. So in other words, what I'm going to do is I'm going to take this thing and I'm going to think about it like this. 2 times 5, that's supposed to be a little dot, 2 times 5 times x plus 2 times 3. So even though the way that I originally write it implies that the 5 should multiply the x first, then multiply by 2, I'm actually going to do 2 times 5 first, which is of course 10. Now there's nothing else I can do besides put the x there, and then 2 times 3 is 6. Isn't that nice? Now, what a lot of people will start doing, very understandably, is they'll start just doing, 2 times 5x will be 2 times 5, which is 10. And then, as I like to say, x comes along for the ride, and then 2 times 3 is plus 6. Many of these you can just kind of do in your head that way. I'll write them out to begin with, just so that you see what's going on. Now, my claim is that this expression and this far simpler one are equivalent. Letter B asks us to do the following. Test for equivalency by substituting x equals 3 into both the original expression and the one from letter A. So in other words, if these two expressions are equivalent, I should be able to grab any value of x, I mean literally any value of x, and throw it into this one, throw it into this one, and they should give me the same result. So I just pick one randomly. So why x equals 3? Because I like the number 3, okay? That's why. You could go with x equals 5, x equals 10, etc. to just check to see if you've kind of done this right. So let's first take that x equals 3 and plug it into this expression, which is actually kind of complicated, okay? And we'll see why, right? If I take x equals 3 and I substitute it into this expression, all right, then what I get is the following. I get this. Now this is a little complicated, right? It's not too bad, but it's a little complicated. Keeping in mind, my order of operations says I need to do what's inside the parentheses first, and when I look inside of the parentheses, I have both a multiplication and an addition. So I'm going to do the multiplication first, right? And that's going to give me 15, then the addition, right? So then the addition, 15 plus 3 is 18, and the last thing I want to do is 2 times 18, which is 36. All right? Now, that was a relatively involved calculation because I had to do this multiplication, then this addition, then this multiplication. And I got 36. Think about how much simpler this one's going to be. So let's evaluate that one. Now when I take x equals 3 and I plug it into that expression, let me bring this up a little bit so we've got some more room, move my icon down, I'm going to get 10 times 3 plus 6. Order of operations says I should do the multiplication first. 30 plus 6, do the addition second, gives me that 36. Right. Now, honestly, that doesn't prove that the two expressions are equivalent. It just means they're equivalent for that value of x. But it's good proof that we've done our work right. And in fact, had we not gotten the same value, had we not gotten 36 for both of them, it would have told us we made a mistake, either in coming up with this answer or in doing the evaluation. And maybe we wouldn't know where our mistake was, but we could go back and we could at least look at this one to see if we got it right. All right, let's keep going. Now, it's important to be able to use the distributive property to take expressions like the following and rewrite them in sort of simpler form. So let's take a look at that in exercise number 3. Use the distributive property to write an equivalent expression without parentheses for each of the following. Show the steps in finding your final answer. All right, let's do the first two together and then we'll have you do letter C on your own. Letter A is one that comes up a lot. Something like a number times a variable plus another number. All right, now again, the distributive property just says I should multiply both things inside of that parentheses by the number 5. All right, so I'm going to kind of make it look exactly the same in both cases, right? 5 times x plus 5 times 2. Now there's absolutely nothing you can do with this except for just write it as 5x, because that's literally what 5 times x means. Now of course 5 times 2 is simply 10. So that's very, very easy. This and this are slightly more complicated. Let's do this one together and have you do this one on your own. So we've got 3 times 4x plus 2, right? So what we're going to do is we're going to distribute that multiplication by 3, and that's going to be 3 times 4x plus 3 times 2. This is now when I can look at this and I can think of it as 3 times 4 times x plus 3 times 2. 3 times 4 is obviously 12, so I just get 12x plus 6. All right. So the only real big difference between this one and this one was that here the x had a coefficient of 4, so we actually had to do 3 times 4 to give me 12x. Here the x has a coefficient of 1, so 5 times x is just 5x. Why don't you pause the video now, use the distributive property to write that product without parentheses. All right, let's do it. Again, simple enough. We're just going to distribute the 9, the multiplication by 9. So we're going to get 9 times 2n, and the distributive property works with subtraction just as well as it does with the division, or addition, sorry. We're then going to take this and really rewrite it as 9 times 2 times n minus 9 times 5. 9 times 2 is 18, 18n minus 45. All right, simple enough. Great. And again, my hope is that you eventually are able to go from here to here without really writing any steps in between. You're able to just look at this and say, I've got 9 times 2n, 9 times 2 is 18, the n comes along for a ride, minus 9 times 5 is 45, done. Now the cool thing is, anything that can be done in math, generally speaking, can kind of be reversed. And what we're going to be looking at in the next couple exercises is how you really reverse the distributive property. So let's take a look at that. All right, reversing the distributive property, always ahead of myself. Exercise number 4. Consider the expression 12x plus 30. What is the greatest common factor, the GCF, of 12 and 30? All right, so I'd like you to pause the video right now because we worked on GCFs earlier this year. Now remember, the greatest common factor of two numbers can also be thought of as the greatest common divisor of the two numbers, the largest number that goes into both of these things sort of nicely, if you will. Pause the video and see if you can figure that out. All right, well, the greatest common factor of 12 and 30 is 6, right? And the reason why, let me just write down the answer, 6. The reason is that 12 is equal to 6 times 2, and 30 is equal to 6 times 5, right? So it is the greatest common factor of the two. And by the way, if you just wrote down 6 and then you didn't write down these two, write down these two. They're going to help us over here, okay? So in letter B, we want to write an equivalent expression by filling in the blanks below. So literally, we are going in the reverse direction of what we did in the last couple exercises. I am undistributing. Specifically, what I'm going to do is I'm going to put the 6 right here. All right? Now, what goes in the blanks? Well, you know, it used to be 12x plus 30. What I want right here is I want what I have to multiply 6 by to get 12x. Well, I know I have to multiply 6 by 2 in order to get the 12. The x will just kind of come along for the ride, right? So 6 times 2x will be 12x. And then, right, I need to know what I need to multiply 6 by in order to get 30. Well, that's the number 5. So, whoops, I already had the x there. My bad. So at the end of the day, what I've got is 6 times 2x plus 5. Right? Make sure that you have that written down just in case the stuff in the blanks is a little confusing. And again, these two expressions in theory are equivalent. Any value of x I take and I plug in should give me the same result between the two of them. And let's actually take a look at that in letter C. Letter C asks us to test to verify these two expressions are equivalent by using the value x equals 2. Test in both the original expression and the one you found in B. All right, so let's just really quickly talk about this for a second. The one that we found in B, the factored expression, because that's what it is called. What we just did is we factored out the GCF is 6 times 2x plus 5. What I'd like you to do is I'd like you to take x equals 2, plug it into this expression, figure out what you get, then plug it into this expression, figure out what you get, and hopefully they're the same thing. Pause the video now and test this equivalency. All right, let's do it. So over here, right, our original expression, we're putting in 2 for x. All right, 12 times 2 is 24. Then I've got to do the addition. Order of operations is so key, right? And I get 54. Now what I'm going to hope is that I also get 54 over here. Now this is going to be a little bit more difficult, but I'm going to put 2 in for x, right? I'm going to work within the parentheses, which says that I've got to do the 2 times 2 first, which is 4, right? Then I'll add that 4 and the 5 together, and that'll be 9. And then 6 times 9 is 54. And that at least gives me some confidence that I did the factoring correctly. So when you multiply a number through parentheses, it's called distributing. When you take the number out and you sort of divide, if you will, that's called factoring. Let's get some practice in this factoring the GCF in the last exercise. Here we go, exercise number 5. Write each of the following as an equivalent product of the expressions GCF and another factor. All right, so the first thing we want to do in each one of these cases is figure out what the GCF is. What is the greatest common factor of all the normal numbers, the coefficients? All right, let's do letter A together. So I'm looking at 7 and 21, right? And I'm thinking to myself, what is the biggest number that divides into both 7 and 21? And that's pretty easy. The GCF in this case is just equal to 7. So that's where I want to start in each one of these problems. Now the question is, what can I write down as an equivalent expression that is a product of the GCF with some other expression? Well, I'm going to write down 7, then I'm going to put down parentheses. Now what I want to look at, I'm going to erase this, is I want to look at this expression. Remember, I want the equivalent expression. I want to think about if I multiplied the 7 through, what would have to be in there to give me 7x plus 21 as a final answer? Well, the first part's quite easy. It's just x. because literally 7 times x would give me 7x. Then plus, and now what times 7 will give me 21? Well, that's 21 divided by 7, right? And that'll be 3. So this and this are equivalent expressions. They're the same expression, but written in different forms. This is known as the factored form of the expression. Let's do another one together, then have you do some on your own. 15n plus 10, right? I want to look at that 15, I want to look at that 10. The biggest number that divides into both, the GCF, is 5. All right? So this one's a little bit more complicated. And the last one, the GCF, was simply the coefficient of the x. Here, the coefficient on the n was 15, so that's definitely not the GCF. But the largest number that divides into both 15 and 10 is 5. So now I'm going to write that down. I'm going to then immediately put parentheses afterwards, and I'm going to think about what has to go in those parentheses. Well, what times 5 gives me 15? That's going to be 3, right? And then I've got to have an n, otherwise there would be no n in my final answer. Now I have plus. Now I'm going to think about what do I have to multiply 5 by to get 10, and that's going to be 2. You can always check your answers by literally doing the distributing. So if I then multiplied through by 5, do I get the original expression? If the answer is yes, then I've done what I should have correctly. If the answer is no, then I botched something. All right? So what I'd like you to do now is pause the video and try to write each one of these in their factored form. All right, letter C can be a tricky one because when I look at 44 and 11, it's probably pretty obvious that the GCF is 11. That is the largest number that divides into both. And now let me write down its factored form. So I'm going to write that 11 down. Now, what do I have to multiply 11 by to get 44? Well, that's easy. That's 4. The y kind of comes along for the ride. Plus, now I think, what do I have to multiply 11 by to get 11? And that's the number 1. A lot of students will somehow forget this, right? They'll think to themselves, well, I factored the 11 out, so it's not there anymore. And then they'll get something silly like 11 times 4y. There won't be any plus 1. But 11 times 4y would be 44y. It wouldn't be 44y plus 11. These two things have to be the same, and you can always check that by multiplying back through. All right, let's play around with some more of them. All right, that might be the hardest one on here. Now the rest of these have subtraction, but subtraction and addition work the same with the distributive property. So 40c minus 16, if I look at the 40 and I look at the 16, the biggest number that divides into both nicely is the number 8. All right, so we've got a GCF, in this case of 8. I write my GCF down. I think, what do I multiply 8 by to get 40? That's going to be 5. The c comes along for the ride. Then I think, what do I multiply 8 by to get 16? And that's going to be 2. All right. If I do letter E, this one's very simplistic. When I look at 18 and 4, the biggest number that divides into both is the number 2, right? So my GCF, not very interesting, is 2. So written in factored form, it's going to be 2 times 9x minus 2. Side note, one way to know that you've got the greatest common factor, and not just, let's say, a common factor, is once you've pulled the GCF out, if you look inside of the parentheses, the two terms in the parentheses should not still have a common factor. So if for here, if I had factored out a 4, that would have been 4 times 10c minus 4. Well, then 10 and 4 would have an additional factor of 2 that could be factored out. So that's how you can tell whether you've got the GCF or just a CF. Let's look at a final one. 60n and 36, and this is a great example because 60 and 36 have a fairly large greatest common factor. That happens to be 12. But you might think, oh, 6, right? 6. Now, in fact, actually, let me just pretend the GCF is 6, right? So if I thought the GCF was equal to 6, then I could write this as 6 times 10n minus 36. Oh, not 10n minus 36. How about just 10n minus 6, right? The problem with this answer, and this expression is definitely equivalent to this one. It's just not the GCF here, but they're definitely equivalent expressions. All right. The problem is 10 and 6 share a common factor of 2. All right. Now I could factor that out, which would then be 6 times 2 times what I'd have left. All right. Or up front, what I really want to do is I want to figure out that the GCF is 12. Okay. And once I know that the GCF is 12, then I can write that down. 12 times 5 is 60, minus 12 times 3 is 36. All right, and that is it. And again, I cannot emphasize enough that every time we do one of these manipulations, what we're doing, whether we're distributing or doing the reverse factoring, is we are producing an expression that is really identical to the original one. It just looks a little different. All right, and by identical, I mean you give me a value of the variable and I plug it into 40c minus 16, or I plug it into 8 times 5c minus 2, they're going to be the same number. The same number. Now, it's very understandable if you say to yourself, well, if they're the same thing and they just look different, why do we even do it? And we're going to get into that more, especially in the next unit. All right. For now, let me just move on to the last slide and kind of summarize the lesson. All right. So today we looked at maybe one of the top 5 most important ideas in all of algebra, and that's the idea of equivalent expressions. 2 algebraic expressions that may look different, but have the same value when you substitute the same value of their variables. All right. We saw how we could use the distributive property to write an equivalent expression using multiplication. We also saw how we could reverse the distributive property in what's known as factoring. All right. We're going to get a lot more work on these in future lessons. For now, I just want to thank you for joining me for another NGen Math 6 lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.